Let's look at the quanta of the B quark and the components associated with its decay. We can start with the electric charge, and we can see that the D part of the electric charge is minus 1/3, and the boson 0 makes no contribution, so that the charge of the B quark is minus 1/3 as indicated by the standard model. Now we can look at the C quark here and see that it is now 2/3, which is indicated by the standard model. And the boson minus, of course, is minus 1. And if we look at the electron-positron pair, we'll see that they have the appropriate electric charges of minus 1 and plus 1, while the weakly interacting massive particle candidate has an electric charge, of course, of 0. Now, once we have the interaction with the positron to create the anti-neutrino, we will see that the electric charge is now 0, as it should be on the neutrino per the standard model. And over here we have a Z boson, and it has no electric charge. Let's look at the spin quanta. The spin quanta for the D quark part of the B quark is plus 1/2, and the boson 0 from the Higgs field contributes no spin. The C quark here, we can see after the emission of the spin 1 boson minus is minus 1/2. And if we look at the electron-positron pair, we'll see that they have opposite spins of minus 1/2 and plus 1/2, whereas the WIMP now has a spin of 0. And if we look at the antineutrino, it now has a spin of 1/2, which is what would be indicated by the standard model for the antineutrino, and the Z particle now has a spin of 1. Let's look at the weak charge. The weak charge on the right-handed D quark is 0, as per the standard model, and the weak charge on the Higgs boson is 0. Now on the C quark, we can see a left-handed C quark has a weak charge of plus 1/2, whereas the boson minus, the W particle here, has a weak charge of minus 1/2. And there is a 0 weak charge here on this pair, so that we can see that the C quark has, left-handed C quark has the appropriate weak charge as per the standard model. And then we have the electron and the anti-electron, and we have weak charges of minus 1/2 and plus 1/2. And on the WIMP, we have a weak charge of 0. Now, if we look at the antineutrino formed out of the interactions here, we will see that the weak charge here is minus 1/2. And so we have a minus 1/2 weak charge on the antineutrino, which, as we know, the neutrino has a weak charge of plus 1/2 when it's left-handed, and this right-handed antineutrino should have the opposite, and it does, of minus 1/2. And on the Z particle, we have a plus 1/2 weak charge because it has a spin of 1. Let's look at isotopic spin. The isotopic spin on the D quark is minus 1/2. But the isotopic spin on the B quark, which includes this boson here, which has an isotopic spin of positive 1/2, then would be 0, as is indicated by the standard model. If we look at the C quark, we can see that we also have an isotopic spin of 0, which is indicated by the standard model, while the W boson minus is carrying away the spin of minus 1/2. Now, on the electron-positron pair, we have isotopic spin of minus 1/2 and plus 1/2. And on the WIMP, we have an isotopic spin of plus 1/2 being carried away by the weakly interacting massive particle. Now, the isotopic spin on the electron, again, of course, is minus 1. And on the neutron, antineutrino, it is also minus 1/2, which is indicated by the standard model. And on the Z boson, we have a weak charge of 0. Let's look at flavor. The flavor on the D quark is 0, but on the boson 0, a flavor charge of minus 1 is being carried, which is the appropriate flavor charge for the B quark. And we see the C quark here has a flavor charge of 1. And the W boson is carrying away a flavor charge of minus 1. The electron and positron have the appropriate 0 flavor charge, whereas the weakly interacting massive particle is carrying away a flavor charge of minus 1. And if we look at the antineutrino, we say that it has a flavor charge also of 0, as well as does the Z boson. Let's look at Rishon number, which supersedes baryon number. And we'll see for the D quark, we have a Rishon number of plus 1/3 and 0 for the Higgs. We have a Rishon number of plus 1/3 for the U quark and 0s for the bosons. And we have a Rishon number for the electron of minus 1 and for the anti-electron of plus 1. And for the antineutrino, we have a Rishon number of plus 1. For the bosons, of course, again, we have a Rishon number of 0. Finally, color charge. We would just look at the color charge for the quarks and see that the color charges are configured as they should be, giving that for the D quark, we should have a color charge of either red, blue, or yellow. In this case, it's yellow because, it's red because the purple anti-T alter-relating Rishon color charge is canceled by the yellow anti-V. And that continues for the U quark because the dual relating anti-V has purple, just as the alter-relating Rishon it exchanged with did. And the electrons have all three colors, anticolors, and then all three colors, and so the antineutrino likewise. And all of the bosons have color and anticolor canceling those out. And so we can see that the quanta are consistent with the quanta that are indicated by the standard model.